Assalamualaikum and a very good morning to everyone. We are from group Me and Me, and today we are going to present our SEL, which is a contractive sequence. Next slide. First of all, we're going to introduce ourselves first. So Fatin, you might begin.
Okay, I am Siti Fatin Natasha, metric number 187322.
My name is Nurul Atika binti Muhammad Razi and my metric number is 203.
My name is Anis Azima binti Muhammad Azman and my metric number 201138.
My name is Nurul Azrin Ardini Muhammad Zohan and my matrix number is 200504.
My name is Nurul Hassana binti Muhammad Razi and my metric number is 2000294.
Alright, so let's begin.
I will first start with task 1. For the question, prove that sequence 1 over n from n equals to 1 to infinity is contractive. Firstly, we need to know a sequence is constructive if there exists a positive number r between 0 and 1 such that the absolute value for sequence n plus 1 minus sequence n less than equals to value of r times 1 times the sequence times the absolute value for sequence n minus sequence n minus 1 for all n equals to 3, and so on. So we'll begin by construction of the first and second term from here. So we'll substitute the n plus 1 and n minus 1 into the sequence. So we'll simplify and obtain for the first term 1 over n times n plus 1, and the second term will obtain 1 over n times n minus 1. So by the definition, we'll try to obtain the r value by dividing the first term by second term, and we'll obtain r more than equals to n minus 1 over n plus 1. We'll then let n equals to 2 because of the definition. So we'll obtain r value more than equals to 1 over 3, and we will choose r more than equals to 1 over 3. Moving on to the proof, we suppose that r is larger or equal to capital R, which is larger than equals to 1 over 3 for n equals to 2. So we'll construct the first and second terms again and substitute into the contractive sequence definition, and then we will substitute that because of r is equals to capital R, so we substitute here, and we will substitute capital R with 1 over 3, where 1 over 3, the positive number r is between 0 and 1, which satisfies the contractive definition. And then since n is equal to 2, we substitute into this equation. We'll obtain 1 over 6 less than or equals to 1 over 6, which is also true, hence the sequence is contractive.
Thank you, Fatin. I will continue for task 2. Given that proof that sequence S equals to set n is not contractive. By definition 1, a sequence of S equals to Sn is said to be contractive if there is a positive number r is greater than 0 and less than 1, such that in modulus Sn plus 1 minus Sn less than or equal to r times in modulus Sn minus Sn minus 1 for all n equals to 2, 3, and so on. We prove this by contradiction. So firstly, we assume S is contractive. We let for R is an element in open bracket 0, 1 such that in modulus Sn plus 1 minus Sn. So Sn plus 1 is equivalent to cert n plus 1 and Sn is equivalent to cert n. Next, this is equals to cert n plus 1 times cert n over cert n minus cert n times cert n minus 1 over cert n minus 1. Here we switch places for each conjugate to maintain the cert. And then we group and then we group it to be cert n plus 1 over cert n times cert n minus cert n over cert n minus 1 times cert n minus 1 in modulus. This line is from previous slide. So then we let Sn equals to cert n and Sn minus 1 equals to cert n minus 1. And then we repeat the same process until we get in modulus cert n squared over cert n times n minus 1 times Sn minus Sn minus 1. And then, as we can see, this line, we put cert n squared over cert n times n minus 1 times Sn minus Sn minus 1 in the same modulus. And it is also equivalent to in modulus cert n squared over n times n minus 1 times modulus Sn minus Sn minus 1. From definition, in modulus, Sn plus 1 minus Sn is less than and equals to R times Sn minus Sn minus 1, then it implies to in modulus Sn plus 1 minus Sn less than in modulus cert n squared times n minus 1 times in modulus Sn minus Sn minus 1. So here we can see R is equals to cert n squared over n times n minus 1. So refer back to our definition. It's that for all n is equals to 2, 3, 4, and so on. And then I take any element of n. So I take n equals to 2. And then I substitute insert n squared over n times n minus 1. I get 1.414213.562. There is contradiction since R is not in element open bracket 0, 1. So here we can see assumption is wrong, since the assumption should be S is contractive, but R is not in element open bracket 0, 1. Hence, we can see that the sequence S equals to cert n is not contractive. Thank you.
So in task 3, we have to prove the lemma 1 by showing that if S is equal to Sn, where n is from 1 to infinity is a contractive sequence, then there exists a positive number R from 0 to 1 such that absolute Sn plus 1 minus Sn less than or equal to R power of n minus 1, absolute S2 minus S1 for n greater than 1. So by using the definition of contractive sequence, where a sequence x is equal to xn for real number is said to be contractive if there exists a constant C element of R, where C is from 0 to 1 such that absolute xn plus 2 minus xn plus 1 less than or equal to C, absolute xn plus 1 minus xn. So for all n in element of n. So in this situation or lemma, we have to use Sn. So we want to prove Sn. So we replace x with Sn. So it's become absolute Sn plus 2 minus Sn minus 1 or less than R. In this situation, we have to use R. Okay. So absolute Sn plus 1 minus Sn. And then it's actually about distance. Absolute Sn plus 1 minus Sn is a distance. So the next step, we want to find the next distance. So what we have to do is R become R power of 2 and then Sn minus Sn minus 1, and then next R power of 3 absolute Sn minus 1 minus Sn minus 2. And then when we actually, okay, we can see here from power of 1, power of 2, and power of 3. And then if we continue, we will get power of until infinity. So we can generalize this, become r power of n, absolute Sn plus 1 minus Sn. So generally, absolute Sn plus 2 minus Sn minus 1, okay, less than or equal to r power of n, absolute S2 minus S1 for n is element of n. So the question wants us to prove lemma 1, in which we have to prove Sn absolute Sn plus 1 minus Sn less than r power n minus 1. So in this situation, r power of n. So what we can do is we have to replace n with n minus 1. So we replace this statement, this equation, into absolute Sn plus 2 minus Sn minus 1. Oh, sorry. We replace n with n minus 1, right? So we replace n minus 1 plus 2, and then continue minus s n minus 1 plus 1. Okay. And then power less than or equal to r. Okay, this one r power of n. So we replace n minus 1 absolute s2 minus s1. So n minus 1 plus 2 is equal to n plus 1. And then Sn n minus 1 plus 1, negative 1 plus 1 is 0. So Sn, so less than or equal to r power of n minus 1. And then absolute S2 minus S1. So the lemma 1 is proven.
So I proceed with task 4 and task 5. So for task 4, proving theorem 1 by showing that limit absolute Sn minus Sn is equals to 0, where n tends to infinity, and hence Sn is Cauchy. So, by the definition of our contractive sequence, we let Sn be a contractive sequence and m is not equal to n. So, we suppose m is strictly greater than n, and there exists r in the element of integers where r is from 0 to 1, such that the absolute Sn minus Sn is equals to absolute Sn plus 1 minus Sn, and this is less or equals to r times Sn minus 1. So now let's say we take n as 2. So we can have that absolute S3 minus S2 less or equals to R times S2 minus S1 following the above pattern. Also, we can have that S4 minus S3 absolute value less or equals to R times S3 minus S2. So we follow the above pattern and we can have that this is less or equals to R times absolute S2 minus S1, since S3 minus S2 is less or equals to R times S2 minus S1. So we can have absolute S4 minus S3 is less or equals to R squared times S2 minus S1. So from here, we can say that in general, absolute Sn minus Sn is strictly in general, we can have that absolute value Sn minus Sn is less or equals to R times Sn minus 1 and less or equals to R squared times Sn minus 1 minus Sn minus 2, and the pattern goes until R to the power of n minus 1 times S2 minus S1. So now we can have this pattern for absolute Sn minus Sn, where absolute Sn minus Sn is actually equals to absolute Sm minus Sm minus 1 plus Sm minus 1 minus Sm minus 2, and the pattern goes until Sn plus 1 minus Sn. So from here, we can observe that this term minus Sm minus 1 and we have plus Sm minus 1, and this cancels each other. and the pattern follows. And this from the triangle inequality, this is less or equals to absolute Sm minus Sm minus 1 separately plus Sm minus 1 minus Sm minus 2 separately plus until Sn plus 1 minus Sn. So now we follow the given pattern of contractive sequence, where the given pattern is absolute Sn plus 1 minus Sn is less or equals to R power of n times absolute S2 minus S1. So from here, we can have absolute Sm minus 1 is actually equals to Sm minus 1 plus 1 minus Sm minus 1 plus 0. Here we just assume that n is equals to m minus 1. Okay, so for this term, we can have that this is less or equals to R power of m minus 1 times S2 minus S1. And for the next term, absolute Sm minus 1 minus Sm minus 2, we have this as equals to absolute Sm minus 2 plus 1 minus Sm minus 2 plus 0. And this is less or equals to R power of m minus 2 times S2 minus S1. And lastly, we can have the term absolute Sn plus 1 minus Sn as less equals to R power of n times S2 minus S1. So we substitute those in the formula that in the formula of Sm minus Sn as before, and we can have that absolute Sm minus Sn is less or equals to R power of m minus 1 times S2 minus S1 plus R power of m minus 2 times S2 minus S1, and the pattern goes until R power of n S2 minus S1 for the last term. Right, so we factorize out the R power, and we can have that in the bracket R power of m minus 1 plus R power of m minus 2 until R power of n, and close the bracket, times S2 minus S1. So from this series of R, we factorize out the R power of n minus 1, and in the bracket, we can have only R power of m minus n plus R power of m minus n minus 1 until R power of negative 1 left in the bracket. So this series is times S2 minus S1 following the above pattern, and we can observe that this is actually the sum of finite geometric series with common ratio R, and the first term is R power of m minus n. So basically, the sum of finite geometric series is strictly less than sum of infinite geometric series. So this is less then R power of n minus 1 times the series of R power of m minus n plus R m minus n minus 1 and until infinity, and this times S2 minus S1. So this is less than the formula of sum of geometric series, where the first term divide by 1 minus the common ratio. So this is strictly less than R power of n minus 1 times R power of m minus n as the first term of the geometric series, divide by 1 minus R as the common ratio of the series, and we times S2 minus S1. So this is strictly less than R n minus 1 times 1 over 1 minus R times S2 minus S1 again, since R is less than 1. So this is just continuation of the previous slide. So this R power of n minus 1 times 1 over 1 minus R times S2 minus S1. So this is just equals to R power of n minus 1 over 1 minus R times S2 minus S1. So now it seems like we can evaluate the limit now. So this limit Sm minus Sn as n goes to infinity is equals to limit R n minus 1 over 1 minus R times S2 minus S1. So we just substitute the n. So R power of n minus 1, as n goes to infinite, is 0 since r is less than 1 and greater than 0. So 0 over 1 minus r times s2 minus s1 is just equals to 0. So therefore, we can show that Sn is a Cauchy sequence. So now for task 5, proving lemma 2, where any Cauchy sequence is convergent. So now we let our Sn be a Cauchy sequence, and Sn is bounded because Cauchy sequences are bounded. So by the Bolzano-Weierstrass theorem, if Sn is bounded, so exists its subsequence, say Snk, that converges say to L. So for all epsilon greater than 0, we have n1 in the element of integers such that absolute Snk minus L is less than epsilon over 2 whenever Nk is greater or equal to N1, since Snk is bounded and Sn is bounded. Now, Sn is Cauchy. So for all epsilon greater than 0, we have N2 in the element of integers where m is not equal to n, such that absolute Sm minus Sn is less than epsilon over 2 whenever m and n is greater or equal to n2. So now we let n is the maximum between n1 and n2. So we choose nk such that nk is greater or equal to n that we chose before. So for all epsilon greater than 0, we have the absolute of Sn minus L is equals to Sn minus Snk plus Snk minus L. This is we put the minus Snk plus Snk to cancel each other, and we want to group this as two terms here. So we can have that absolute Sn minus Snk plus Snk minus L, and by the triangle inequality, we can have this as less or equals to Sn minus Snk plus Snk minus L. So from the previous slide, we have this as less to epsilon over 2, and we have Sn minus k also less than epsilon over 2. So this for the following term, we can have less than epsilon over 2 plus epsilon over 2, and this is equals to epsilon whenever n is greater or equal to n, and nk is greater or equal to n also. So therefore, we can say that every Cauchy sequence is convergent.
Prove any contractive sequence is convergent. So the corollary is if x is equal to xn is a Cauchy sequence with a constancy where c is between 0 and 1 and limit x equal to x, then we can write it as like the number 1 or the number 2. So the theorem is every contractive sequence is Cauchy sequence, thus it is convergent. So right now we will prove the sequence to be a Cauchy, and thus we can assume it is convergent. Let x equal to xn be a contractive sequence for all n in natural numbers. Then exists a constancy that lies between 0 and 1 such that modulus xn plus 2 minus sn plus 1 smaller or equal to c modulus xn plus 1 minus xn for all n in n. And then we can write for n equal to n minus 1, n minus 2, n minus 3, and so on. We can write it as modulus xn plus 2 minus xn plus 1 smaller or equal to c xn plus 1 minus xn equal or smaller c square modulus xn minus xn minus 1, and then the last one can get c power of n x2 minus x1, because we can see here that if we subtract each of these sequence, we can get x. That's why we can write x. x2 minus x1. So now without loss, the generality for m is bigger than n is equal to m minus 1, which is mn is n. So modulus xm minus xn is smaller or equal to modulus xm minus 1 plus modulus xm minus 1 minus xm minus 2, and so on. We can get xn minus xn plus 1. So we can apply this thing into this. You can get c power of m minus 2 modulus x2 minus x1 plus c power of m minus 3 modulus x2 minus x1. You can get lastly is c power of n minus 1 modulus x2 minus x1. So we can factorize it. We can and lastly we can get c power of n minus 1 in bracket c power of m minus n minus 1 and so on. And the outside we can get modulus x2 minus x1. So okay, if we apply geometric series formula, which is a in bracket 1 minus r over 1 minus r, which is the a is over here, we can get c power of n minus 1, and the r is c power of m minus n. So we can write the geometric series like this for c between 0 and 1. So we can get smaller and equal c power of n minus 1, 1 over 1 minus c modulus x2 minus x1 is approaching to 0 as n is increasing to infinity. So we can get modulus xn minus xn is equal to 0. Hence, xn is a Cauchy sequence, and therefore, by Cauchy convergence criteria, xn is a convergent sequence. So we are going to conclude what we have learned and what we have got from this SCL, which is contractive sequence. So the first is we learn to use the definition of contractive sequence to prove its properties. And the second one is we learn to prove a sequence is contractive by construction. And the third one is we learn to prove a sequence which is not contractive by contradiction. And lastly is we learn to apply the theorem which is contractive sequence is Cauchy sequence, thus it is convergent. Thank you.